This is ELC131, Circuit Analysis 1, and this presentation is on parallel RC circuits. Impedance, symbolized by the letter Z, is measured in ohms, and the unit symbol is the Greek letter omega. Impedance is the opposition to alternating current, and it is a combination of resistance and reactance. Reactance is the frequency-dependent opposition to a sinusoidal alternating current from an inductor, X sub L, or a capacitor, X sub C. Now let's look at the phase relationships of a parallel RC circuit. Now, in a parallel RC circuit, such as that shown in Figure 1, all the voltages are the same. V source equals VC1 equals VR1. And these voltages are the same in both magnitude and time. So with this parallel RC circuit, we're going to use voltage as our reference. And we see this illustrated in Figure 2, that the source voltage starts at 0 volts at 0 degrees. Now, there's no difference in time between when a voltage is applied to and current flows through a purely resistive element. So V source and IR happen at the same time as shown in Figure 3. However, from our discussions of the action of capacitors, you recall that current leads voltage by 90 degrees in a capacitor. So referring to Figure 4, we see that the capacitive current happens 90 degrees before the resistive current and the source voltage. Now, it's difficult to illustrate this phase relationship between the capacitive current and the resistive current by sketching the sine waves. So we use a vector diagram to illustrate this phase relationship. So referring to the vector diagram of Figure 5, we see that the resistive current and the source voltage are placed at 0 degrees on the vector diagram. This is our reference point. And the capacitive current, IC, is placed at positive 90 degrees. Now, Kirchhoff's current law states that in the circuit of Figure 1, I source equals IR plus IC. But IR and IC do not happen at the same time, so they cannot be added directly. They must be added as vector quantities. So mathematically, I source equals the square root of IR squared plus IC squared. I source is the hypotenuse of a right triangle with the two sides of the triangle being IR and IC, as illustrated in Figure 6. And with these circuits, we're concerned about the angular difference between the source current and the resistive current, which is the angular difference between the source current and the source voltage. This is the phase angle of the circuit, symbolized with the Greek letter theta. Mathematically, theta equals the inverse tangent of IC over IR, the inverse tangent of the side opposite to theta divided by the side of the triangle that is adjacent to theta. Now, the impedance of a parallel RC circuit can be calculated several different ways. We can calculate impedance by using Ohm's Law, Z equals Vs over Is. We can calculate the impedance of a parallel RC circuit using the product over sum equation. Z equals R times X sub C divided by the square root of R squared plus X sub C squared. Again, we cannot add R and X sub C directly. We must add them as vector quantities. And just like parallel resistive circuits, I can calculate the total opposition to current using the reciprocal formula. Impedance equals 1 over the square root of 1 over R squared plus 1 over X sub C squared. And for a parallel RC circuit, I can also calculate impedance by finding the reciprocal of admittance. So the reciprocal of reactance is susceptance, symbolized with the letter B, and it's measured in Siemens. The reciprocal, so B sub C equals 1 over X sub C. The reciprocal of resistance is conductance, symbolized with the letter G, and this is measured in Siemens. G equals 1 over R. And from our rules of polar math, we recall that when we divide polar quantities, the magnitudes divide and the angles subtract. So 1 over X sub C at negative 90 degrees gives us B sub C at positive 90 degrees. 1 over resistance at 0 degrees gives us conductance G at 0 degrees. And this is illustrated in Figure 7 and Figure 8. So the admittance of a parallel RC circuit, admittance symbolized with the letter Y, measured in Siemens, admittance equals the vector sum of G and B sub C. Y equals the square root of G squared plus B sub C squared. And the phase angle is the inverse tangent of B sub C over G. And of course, Z equals 1 over I, so referring to the vector diagram shown in Figure 8, if Y is in the first quadrant, Z will be in the fourth quadrant. Now let's analyze the circuit of Figure 1. So the first step in the analysis of the circuit is to find the value for capacitive reactance. X sub C equals 1 over 2 pi FC. So for the circuit of Figure 1, X sub C equals 159 ohms. Then we're going to calculate the branch currents IC and IR. Now note in these calculations I've converted the source voltage of 1.41 volts peak to an RMS value of 1 volt. So IC equals V source over X sub C, which is 6.29 milliamps. IR equals V source divided by R, which gives us 5.56 milliamps. Now the source current for Figure 1 is the square root of IR squared plus IC squared, which is 8.4 milliamps. And the phase angle of the circuit is the inverse tangent of IC over IR, which is 48.5 degrees. And the current vector diagram for the circuit of Figure 1 is shown in Figure 9. Now, again, we can calculate impedance through several methods. The first we show is using Ohm's Law. Impedance equals V source over I source, 1 volt divided by 840 milliamps, which equals 119 ohms. We can also calculate impedance using the product over sum formula, 180 ohms times 159 ohms divided by the square root of 180 ohms squared plus 159 ohms squared gives us 119 ohms also. And we can also use the reciprocal formula to calculate impedance. 1 over the square root of 1 over r squared plus 1 over x sub c squared gives us 119 ohms. And lastly, we can find impedance by finding the reciprocal of admittance. 1 over 840 millisiemens at 48.5 degrees gives us 119 ohms at negative 48.5 degrees. And we see here the equations, or the equations to find the admittance of the circuit, where again B sub C equals 1 over X sub C, which is 6.29 millisiemens. Conductance is 1 over R, which is 5.56 millisiemens. Admittance, Y, equals the vector sum of G and B sub C, which is 8.40 millisiemens. And the phase angle for admittance is the inverse tangent of B sub C over G, which is 48.5 degrees. The admittance vector diagram of figure 1 is shown in figure 10. So note, looking at figure 10, that admittance is in the first quadrant. This is the same quadrant as I source, and the impedance is in the fourth quadrant, which makes sense because impedance is a combination of R at 0 degrees and X sub C at negative 90 degrees.